All right, you are welcome again. Today, let's talk about Bernoulli Differential Equation. That is differential equation or ordinary differential equation that are said to be Bernoulli. Okay, now we say that any equation of this form, dy dx plus py equal to qy raised to power n. The n can be anything. Let's call this equation 1. So anytime we have an equation that is of a bit complex than the linear differential equation that is in this form, dy dx plus py equal to qy raised to power n. So we say where p and q are function of x or constants, say that this equation is called Bernoulli equation. We say that this equation is called Bernoulli equation. Now, please pay attention. The logic here is very simple. What we do here is we reduce this Bernoulli equation to linear differential equation and then solve. That's just it. We reduce it to linear differential equation and then we do what? We solve it. That is it. But please pay attention. Let me explain how we try to reduce it to linear differential equation. Okay, now though it's not necessary, but after explaining, we are going to take an example and then we see how it is being done. Now let's go. We say we want to reduce it to linear differential equation. Now, what makes this equation not to look like linear differential equation? It is only the right hand side, which is qy raised to power n. So now let's start by making q to stand alone. That is, we want to stripe everything that is associated with this q. How can we remove this? That means we multiply this right hand side by 1 all over y raised to power n. That is the inverse of that associate or the inverse of that coefficient. Okay, so and then whatsoever you do to the right hand side, also do to the left. So that means we multiply both sides by 1 all over y raised to power n. And then you discover that this 1 all over y raised to power n is the same as y raised to power minus n. Hello, it's the same as y raised to power minus n. So we can say we multiply both sides by y raised to power minus n. Now when we do so, we're going to have y raised to power minus n times dy dx plus py times y raised to power minus n equal to qy raised to power n times y raised to power minus n. All right, good. So when we multiply, we see that we're going to have y raised to power minus n dy dx plus py 1 minus n. When we say y times y raised to power minus n, this ordinary y is y raised to power 1. And then since in the law of indices we have the same base, we just add their exponent. So that means we have 1 minus n. Okay, then we have equal to q. Now let's call this equation 2. Please pay attention step by step as we go. Let's call this equation 2. From here, we're going to say let y raised to power 1 minus n be called the letter z. We are trying to make it to look like a very simple linear differential equation. And we are going to succeed. So let's we have succeeded in making q to stand alone. Is that true? Yes. Now let's go to p now. You see, we want to make q to stand alone, and then you see that dy dx and p now has coefficients. Now let's also do something about them. We are going to say let y raised to power 1 minus n be called the letter z. Okay, now as we say let it be called the letter z, let's differentiate this z with respect to x. Hello, let's do what? Differentiate this z with respect to x. That means we are going to bring down the power in front of the y and then subtract 1 from the power. That is the differentiation. And then you know that this is implicit. Then we add dy dx because we are actually differentiating y with respect to x. So when we differentiate this y raised to power 1 minus n with respect to x, is going to give us 1 minus n in bracket y raised to power 1 minus n minus 1. Okay, so you say 1 minus 1 is going to give us 0. Then we have minus n. Then you add dy dx because we differentiated this y with respect to x. Is that clear? Yes. Now let's go. So after this differentiation, we have dz all over dx is equal to 1 minus n in bracket y raised to power n dy dx. Let's call this equation 3. Let's call this equation 3. Now let's go back to equation 2. Our equation 2 says y raised to power minus n dy dx plus p y raised to power 1 minus n equal to q. Let's multiply this equation by 1 minus n. Let's multiply this equation by 1 minus n. So when we do so, we're going to have 1 minus n in bracket y raised to power minus n dy dx plus 1 minus n in bracket p y raised to power 1 minus n equal to 1 minus n multiplied by q. Let's call this equation 4. Let's call this equation 4. So as we call this equation 4, please look at this equation very, very careful. Look at it carefully. From this place, you know we said let y raised to power 1 minus n be called the letter z. You can see it here, right? Good. And then as we say z equal to y raised to power 1 minus n, then we say let's differentiate this z with respect to x. And then we end up having 1 minus n in bracket y raised to power minus n dy dx. You get it right? Good. Now, from this equation 4, you can see clearly that we have something in common, like equation 3. You see it. This first term, we have 1 minus n in bracket y raised to power n dy dx. It's the same thing as what we have in equation 3. So we are going to substitute it with dz dx. You get it right? Good. So we said substituting equation 3 into equation 4. That means we're going to have dz dx. That is in place of this 1 minus n. You get it? So substitute it with dz all over dx plus 1 minus n in bracket p y raised to power 1 minus n equal to 1 minus n in bracket q. Also, this y raised to power 1 minus n, let's replace it with z. Okay, now replacing it now, we say dz all over dx plus 1 minus n pz equal to 1 minus n in bracket q. You get it right? Good. From this place now, we see setting 1 minus n in bracket p to be called p1 and 1 minus n in bracket q to be called q1. So anywhere we see 1 minus n in bracket p, we replace it with p1. And anywhere we see 1 minus n in bracket q, we replace it with q1. So we are going to have the z all over the x plus p1z equal to q1. Hello. The z all over the x plus p1z equal to q1. Is it not the same as linear differential equation? It's the same. It's the same. So from here we say where p1 and q1 are functions of x or constants, and these can now be solved using integrating factor. Finally, having found z, we convert it back to y using z is equal to y raised to power 1 minus n. Hello. Now, let me just show you some simple steps for us to take using this example. Please pay attention. I just explained how we are going to do it. That is, we have a Bernoulli equation. We try to change it to linear differential equation, right? Good. Let's take a look at this example. And then please follow me gradually. Let me solve it in a very simple and systematic way. All right, good. Now let's go. Solve this Bernoulli equation. Solve this Bernoulli equation. dy dx plus 1 all over x y equal to x y raised to power 2. We have dy dx plus 1 all over xy equal to xy squared equal to xy squared. All right, good. Let's call this equation 1. The first thing we say we want to do is we want to make it look like a linear differential form. And what disqualifies this equation from being linear differential form is this y squared. So we want to remove this y squared. First, to remove this y squared, we multiply through by y raised to power minus 2. Pay attention to this y raised to power minus 2. Okay? So when we multiply through, what are we going to have? We're going to have y raised to power minus 2 times dy dx plus 1 over x y times y raised to power minus 2 equal to xy squared times y raised to power minus 2. So when we perform the operation, we are going to see that y raised to power minus 2 dy dx plus 1 all over x. This place we say y times y raised to power minus 2 is the same thing as saying 1 minus 2. So when you say 1 minus 2 is minus 1, okay? So that's why we have 1 all over x in bracket y raised to power minus 1. And then in the right hand side, we only have x remaining. Okay, good. So the next thing we are going to do is we are going to multiply through by 1 minus n. We are going to multiply through by 1 minus n. And then you remember what n is. N is the power of y. Okay, and then the power of y is 2. So our n is 2. So that means we're going to have 1 minus 2. We multiply through by 1 minus 2. And then when you say 1 minus 2 is what? Minus 1. So that means we multiply through by minus 1. Okay? This equation 2 that we have, we multiply it by minus 1. So when we do so, that means we're going to have minus 1 in bracket multiplied by y raised to power minus 2 dy dx plus we have minus 1 multiplied by 1 over x in brackets y raised to power minus 1 equal to, this is minus 1 times x is going to give us minus x. Let's call this equation 3. All right, good. From here now, this y raised to power minus 1 in the center, let's call it a letter z. Let's call it a letter z. Okay, good. But before that, let's differentiate this z with respect to x. That means we're going to say the z all over the x. So we're going to bring the minus 1 down and then subtract minus 1 from minus 1. So that means we're going to have minus 1 in bracket y raised to power minus 2. When you say minus 1, it's going to give you minus 2. Then because we differentiate y with respect to x, we add dy dx. Okay, so here we have the z all over the x is equal to minus 1 in bracket y raised to power minus 2 dy dx. Okay, good. Now, in equation 3, look at it very well. In equation 3, look at it very well. We have minus 1 in bracket y raised to power minus 2 dy dx. And then we have a new value, dz all over dx is equal to the same thing we have here. So in place of this minus 1, y raised to power minus 2 dy dx, we replace it with dz dx. We replace it with dz dx. So let's go. We have dz all over dx minus, we have 1 all over x. This y raised to power minus 1, we replace it with z. Is that true? Yes. Then equal to minus x. So we see that our equation have now reduced to linear differential form, which is dz all over dx minus 1 all over x multiplied by z equal to minus x. This is the same form of linear differential form. And then if it is the same, we see that p is equal to minus 1 all over x and q is equal to minus x. So since we have p is equal to minus 1 all over x, let's integrate p with respect to x. So that means we're going to have the integral of p dx. We integrate minus 1 all over x with respect to x. So when we do so, we're going to have minus ln x. We're going to have minus ln x. Now let's go. Let's find the integrating factor. The integrating factor says e raised to power the integral of p dx. And we have solved and we found p, the integral of p dx to be minus ln x. That means we're going to take the exponent of it. So we're going to say the exponent of minus ln x, or we say e raised to power minus ln x. Okay, so this e raised to power minus ln x is the same thing as saying 1 all over e raised to power ln x. So this e raised to power ln x is the same thing as saying x. The exponent will cancel the ln. Okay, so we're going to be left with x. So here we have 1 all over x. Our integrating factor is 1 all over x. Our integrating factor is 1 all over x. All right, good. Now, when we have linear differential equation where we have dy dx, we make use of y, right? But in this case, we have dz dx, then we make use of z. Hello. In linear differential equation, we have dy dx. That's why we make use of y. But in this Bernoulli, we replaced y with z. That means we are solving for z. That means we are what? Solving for z. Now, the same procedure we used in solving linear differential, where we say y multiplied by the integrating factor equal to the integral of q multiplied by the integrating factor dx, is the same, but the only thing that changes is y changes to z. So that means we're going to say that our solution is z multiplied by the integrating factor equal to the integral of q multiplied by the integrating factor dx. The solution is z multiplied by the integrating factor equal to the integral of q multiplied by the integrating factor dx. You get it right? Good. So the integrating factor we have is 1 all over x. So we have z multiplied by 1 all over x is equal to, we have the integral of our q is minus x. So we have minus x multiplied by 1 all over x dx. So when we say minus x multiplied by 1 all over x, we have minus x all over x, which is equal to minus 1. So here we have the integral of minus dx. So when we integrate, it's going to give us minus x plus c. So here we have z 1 all over x is equal to minus x plus c. All right. You know, we are looking for z. All right. So we make z the subject. So how can we make z the subject? We want to stripe this coefficient 1 all over x. So we multiply both sides by x. So we multiply both sides by x. We are going to have z is equal to x open bracket minus x plus c. So use this x to open the bracket. We are going to have cx minus x squared. I'm going to say that z is equal to cx minus x squared. When you say x multiplied by minus x, it's going to give you minus x squared. And when you say x multiplied by c, it's going to give you cx. All right? Good. But you remember that z is equal to y raised to power minus 1. Hello? You remember that z is equal to y raised to power minus 1. You remember? Yes. Now, we want to replace the z with the value y raised to power minus 1. So when we replace it, that means we're going to have, in place of this z, we'll replace it with y raised to power minus 1. So we have y raised to power minus 1 is equal to cx minus x squared. Is equal to what? Cx minus x squared. We are looking for y, not the inverse of y. So we take the inverse of both sides. We take the what? The inverse of both sides. Or we just transfer the inverse from this side to the other side. So we're going to say that y is equal to cx minus x squared, all in bracket, raised to power minus 1. We simply say cx minus x squared, in bracket, raised to power minus 1. All right? Yes. So the solution to the Bernoulli equation is y is equal to cx minus x squared, all in bracket, raised to power minus 1. Now, we have discussed about this Bernoulli. The logic there is trying to change the equation to linear differential. So by so doing, y we change to z, and then in place of dy dx is going to be replaced with dz dx, and then we solve for z. After that, we replace z with the original value of y, and then solve for proper value of y. All right? Yes. Thank you very much for watching. I hope you enjoyed this video. Let's take more examples so that you understand better. Thank you. Please subscribe if you have not. Like and share our videos. Stay blessed.